Good afternoon. So, this is lecture number 32, and today we will talk about uncertainty analysis and general experimental procedures. Okay, so if you recall from the previous lecture, a little bit idea about uncertainty I had given. So, let me repeat that again. So, typically, when we do experiments, there are certain things which are typically called as errors, and there are some things which are called as uncertainties. Okay, so errors in measurements are because of some known reasons, and one of the known reasons, say I told you that if we are doing some mistake in using the instrument, for example, if we are not fixing wires properly, if we are keeping some power supply of the instrument not switched on, so because of that, whatever the errors will be in our measurements, these are called as actually gross blunders. Okay, then second type of error is which may come majorly because of the calibration of the instrument. That is something which comes as a fixed error. Okay, and fixed error or biased error. So for all these errors, actually reasons are kind of known. Then one more type of error is which is called as random error. So random error means which is coming because of the human errors and some other things which are happening, which are not in our control, and we don't know the reasons for these random errors. So once we have this type of random error, so what will be happening, say if you are making measurement of pressure by using some instrument, you will not always get the same value of pressure. Say you are getting different value of pressure in 10 different measurements. Okay, so because of which you can define some accuracy of your measurement, and majority of the time accuracy of measurement is actually itself associated with the instrument. So whenever you purchase an instrument, with that you will be finding, say its full range of measurement is say from 0 to 100 pascals. Along with that, it will be given that it is having say plus minus 2 pascals measurement error, or say plus minus 1% measurement error. So that is nothing but comes under the uncertainty limits of that particular instrument. Okay, because you cannot control that, you don't know the exact reason because of which that is coming in your measurement. Okay, so typically whatever we measure from any instrument, that is not 100% true, that is true within certain range. So whenever we measure something, of course that parameter, in many cases it may happen that say we are able to directly use that parameter in our output, but many times it will be happening that whatever the measurement we are doing, these will be acting as primary measurement points to derive some other output parameters. Okay, for example, if you have to measure power, so if you are measuring voltage and current, so then voltage and current are your primary measurement parameters, but whatever you want to say represent for your final parameter for understanding the characteristics of some system, then say power is my required output variable. So power I will be calculating as product of voltage into current. So if I have some uncertainty in the measurement of voltage and in the measurement of the current, so it means in independent parameters, then ultimately out of these measurement instruments, whatever power I am obtaining, in that also I will be having some amount of uncertainty. Okay, so how to calculate that uncertainty in the output parameter if it is there in our input parameter, that is something which we want to see over here, and it is typically called as uncertainty analysis. Okay, so say my measurement of power, measurement of voltage by some instrument for a given condition is 100 volts plus minus 2 volt, and measurement of current is 10 ampere plus minus 0.2 ampere. Okay, now if you are asked to calculate the power and uncertainty in power, so typically the value of power we can simply think as E into I, so I can simply say it is 1000 watt. Okay, but of course as I told you that in power also there will be some uncertainty. Okay, so what thing can come to immediately our mind, that say if I talk about the maximum positive deviation in the measurement of voltage, so maximum positive deviation in the measurement of voltage will lead to value 102 volt, and maximum positive deviation in the measurement of current will lead to a value of 10.2 amperes. this. Okay. So one thing can come to my mind, that if I just simply multiply the maximum positive deviations of all the independent parameters and use these in the final formulation of power, say that is my maximum deviation in power which I will be getting. Then similar thing I can do, that I will take the smallest value considering the negative deviations in the measurement of individual quantities, maximum deviations in the measurement of quantities, and then simply use these to calculate the output parameter. So what I can get, that maximum power out of this will be say 1040.4 watt and 960.4 watt. Okay, but say my true measurement is nothing but 1000 watt. So with reference to the true measurement, you can see that you have plus 4.04% in uncertainty in positive side and minus 3.96% uncertainty in negative side. So this is nothing but some rough or gross estimate of uncertainty in measurement of power, which is derived from the voltage and the current. So that is something which comes to our mind. But now in this there is one important issue. The issue is, when we are talking about uncertainty, okay, there is very less or even extremely impossible situation or extremely less probability that when I am having maximum positive deviation in the voltage, corresponding to that I will also get maximum positive deviation in the current. So probability of occurrence of this type of event is extremely low. Okay, so if this probability is extremely low, then if I use this method for estimation of the uncertainty, obviously it will be giving me the large band of uncertainty. Okay, so my measurements will be having significant amount of uncertainty. Okay, so that's why this particular method cannot be considered to be true representative of the uncertainty of the output. Okay, so from our common sense it may appear to us that we are able to calculate the maximum deviations and maximum to minimum range in the measurement of power, but ultimately the chances of occurring the deviations at maximum deviations at the same point of time in all the instruments is actually rare. Okay, so that's why we have to use some other method. So how that method works, that I will now show you. So let me consider that x1, x2, x3, xn are nothing but n number of independent parameters for which actually we have done measurement. And R is my final output parameter, which is the function of these independent measurements x1, x2, x3 and xn. Okay. So as per the method of Klein and McClintock, if W1 is uncertainty in measurement of parameter x1, W2 is uncertainty in measurement of parameter x2. Likewise, I have Wn are the individual values of the uncertainties in each measurement parameter, measured parameter. Okay. So then the total uncertainty in the resultant can be written in terms of del R by del x1 times w1 and whole square of this plus del R by del x2, like variation of R with x2. How much your resultant is changing upon change in x2. So rate of change of resultant parameter with rate of change of that individual parameter into measurement, into uncertainty in that parameter. Okay, whole square likewise, and then square root of the entire quantity. So this will be nothing but my uncertainty in the resultant. Is this point clear? So now if I use this particular method to calculate the uncertainty in power, if I know these two individual uncertainties. So this is nothing but my W1 and this is W2. Okay. So now, and formula of power is E into I. So functional relationship is given. So now can you calculate uncertainty using this method? So if you calculate, then what is the value of uncertainty you are getting? Can you tell me? Please calculate it. So once you need to calculate del P by del E. What is del P by del E? I. And then del P by del I, which is nothing but E. Then you can simply say that uncertainty in resultant is I into omega 1 W1 square, okay, and then plus E into W2 entire square and then the square root of the entire quantity. So if you do so, and then, so this will be your value of uncertainty in measurement of absolute value of uncertainty in measurement of power. But if you now calculate this WR by R, okay, then what you will be doing, you will be dividing this entire equation by R, and ultimately you can calculate the value of uncertainty in percentage. Okay, so if you calculate the value of uncertainty in percentage, you will be getting it to be 2.83%. Is this point clear? So now here you can see that this value of uncertainty in measurement of power is less in comparison to the values of uncertainties which we have calculated based on the occurrence of maximum and minimum deviations simultaneously in all the parameters. Okay, is this point clear? So this is obvious reason, because as I told you, the chances of occurrence of maximum deviations in both the parameters simultaneously or minimum deviations in all parameters simultaneously are actually extremely less. Okay, so because of which we have to follow this type of procedure. Okay, so this is generalized equation. This can be applied for any type of system, like you can have functional form in any form, say additive form or multiplication form. Okay, so in the subsequent slides some standard functional forms are taken and then this formula is actually deduced. So that is the same formula, just you have to simply deduce this in the final form. So say if your resultant is in terms of x1 power a1, x2 power a2 and xn power an, where a1, a2, an are nothing but some constant power exponents. Okay, and x1, x2, xn are nothing but your measurement parameters. Okay, so then if you have to apply the previous formulation, what you need to do? You need to calculate this del r by del x1, del r by del x2. So in order to generalize this, I have used exponent I. So if you consider any value this xi power ai, then you will be finding when you are taking derivative corresponding to this value, so this is a partial derivative, all other parameter will be coming as a constant. So out of the derivative, so x1 a1, x2 a2, so on up to xn an, and the derivative of xi will become ai into xi ai minus 1. Okay, now what I can do, I can use this formulation in my previous formula, and then so previous formula tells that if I have to calculate my uncertainty in terms of percentage, then I need to write WR by R. Okay, so if I calculate WR by R, then inside when I am using this del R by del Xi into x into Wi whole square, it will be multiplied with 1 by R. Okay, here also I will be using this, also I will use 1 by R square, because everything outside I am using 1 by 2. Okay, so now what I can do, I can simply calculate 1 by R into del R by del Xi. If I calculate this, then I get ai by xi. Okay, and ultimately my overall uncertainty can come as summation over ai w xi divided by xi whole square at whole power 1 by 2. Is this point clear? So if you have your output in terms of this type of standard function where you have the actually product function involved with the powers, then you can calculate using this standard formula your answer. Okay. Then second is if you have say additive function. So in case of additive function, what will be happening now? Del r by del xi will become simply equal to ai, and then your final uncertainty will become ai wxi square into 1 by, okay. So this is not in percentage, this is the absolute value of the uncertainty. Is this point clear? This is very simple mathematics. Okay, now comes one important point, and this will give you idea that when you plan your experiment, then what type of measurements you should choose. Say if you have choice among different measurement parameters, then what type of measurements you should make. So that's why the heading is selection of measurement method. For example, if you are calculating power, okay, so for calculating power from a circuit, if you can do measurements of resistance, you can do measurements of voltage, and you can do measurements of current. Now you have three different options. You have voltage measurement device also, current measurement device also, and resistance measurement device also. But you have to calculate power. So you have multiple methods. You can calculate power equal to E into I. You can calculate power equal to V square by R. You can calculate power equal to I square into R. So it means either you can use the measurement of current or resistance, either you can use the measurement of voltage or resistance, or you can use voltage and current. Okay, so you have multiple combinations. Now let's consider that my voltmeter is having uncertainty of plus minus 1%. Emitter is having plus minus 1%, and also resistor is also having plus minus 1%. Okay, so now the first method is say E square by R, and second method I am using E into I. So it means in first method I am trying to use the measurement of voltage and resistance. In second case I want to use voltage and current. So out of these two, which one will be favorable? So if I used first method, then first I will be using del P by del E, which is becoming 2E by R, and del P by del R, which is becoming minus E square by R square. And using this method, this will be my final formulation of uncertainty in measurement of power. Okay. If you calculate uncertainty using this method, you will be getting it in the range of 2.236%. Okay. Now if you use the second method, so in second method you will be using del P by del E, which is I, and del P by del I is E, and then you will apply this formula, and ultimately you are getting uncertainty 1.414%. Okay. So which is giving you least uncertainty? Voltage and current. So it means that if you have choice that you can measure resistance also, you can measure current also, voltage also, and using these three parameters you have to calculate the output power. So which parameter you will be choosing? Voltage and current, because that will be giving you the less amount of uncertainty in your measurement. Okay, so of course, but if you have some uncertainty in resistance, ultimately that is changing your current also. Okay, so that is already accounted in that measurement of current. Okay, so this is the meaning is ultimately whatever value you are obtaining, that is influenced by uncertainty in one type of measurement. But ultimately in your output formulation, that depends upon the nature of this resultant function. Okay, so depending upon the nature of resultant function, in your output there can be, by one method there can be amplification of uncertainty, in second functional form there can be diminishing of the uncertainty value. So that depends upon the functional form. So which functional form, which measurement we have to use, that is something which we can select a priori, like before developing the experimental setup. Okay, so uncertainty analysis is something which at this moment in your mind it may appear that first thing what we need to do, we need to develop the setup, and after that what we will be doing? We will be making some measurements, and then whatever our results are coming, we will show that in our results this much uncertainty is there. But this is not the approach. The approach is just completely in the reverse direction. You have to start first from the very first thing. Whenever you will be designing some experimental setup, first you have to identify that what measurements you want to make, and then these measurements you want to make in under which range of measurement. Once you have decided the range of measurement, say you want to measure flow rate, you have decided that in your experiment you will be controlling flow rate from 0 to 100 LPM. Okay, so you will be choosing flow meter as per that. Once you have chosen the flow meter, then corresponding to that flow meter, from the data sheet of the flow meter, you will be having some uncertainty mentioned over there, plus minus 1% or 2% or so. Okay, so likewise you have say flow rate, you have some other uncertainty in measurement of some second parameter, third parameter. Then what you will be doing, when you will be using these parameters to calculate your resultant, then whatever the formulas are available, first you will be identifying all the formulas from your theoretical framework. Okay, and then using these formulas for measurement of the output, you will be first doing the uncertainty analysis. And once you have done uncertainty analysis, that will be telling you that if you choose this method of measurement, then this much uncertainty you will be having in your output. If you choose second method, then this much uncertainty. Third method, then this much uncertainty. Then you have to choose the method which is giving you the less amount of uncertainty. But of course, you are not always going for that method. Many times you are also limited by the cost of the instrument. So financial case. Okay. So that all comes in the planning of the experiment. So what are the things we need to follow in the planning of the experiment, that I will show you in the subsequent discussion. Okay. But this is important, that uncertainty analysis is something, of course, whenever you are presenting the results, you have to mention there that how much uncertainty is there in your results. But uncertainty analysis, before deciding the instruments for your experimental setup, you have to perform this, and then based on that actually you have to choose the methods of measurement. Okay, then of course when you have say number of parameters are less, then estimation of uncertainty is actually simple. Say you have 5 parameter, 10 parameter, or even 15, then also you can do the measurements. But say in some case you have 100 parameters. Okay, so when you have 100 parameters, then if you use this type of functional form in between 100 variables, it may be extremely challenging to do that. So what we can do, we can actually take the help of computers to just write a simple code, and with the help of that code, if we have data of 100 variables, we can calculate the value of uncertainty. So how to do that? Let's try to see that. So our now main interest is to estimate the uncertainties for complicated data reduction, where you have actually significant amount of data available. So there what you can do, say my resultant variable, when I have simply considered x1, then it is like this. Okay, when I am doing small perturbation in x1, if I am doing small perturbation in x1, the meaning is I have deviated the value of x1 by delta x, then I will be getting r x1 plus delta x1. So say here only this first functional form will change and all others will remain the same. Likewise I can do by considering each and every parameter all the time. So say second time I have taken x2, and then this deviation is x2 plus delta x2. Okay. Now, if I have to calculate del r by del x1, what will be del r by del x1? I can write it r of x1 plus delta x1 minus r x1 by delta x1 when I am considering the order of accuracy to be first. Okay. Then when I am using this, so likewise I can do this, but over here in everything, here order of accuracy is delta x1, here order of accuracy is of the order of delta x2. Okay. So after I have calculated these delta r by del x1, delta r by del x2, ultimately what I need to do now? I need to calculate uncertainty resultant. So I simply need to supply these values and then their individual uncertainty and then square of that. Okay, so that I can simply substitute into that formula. Okay, so it means that if I have large number of data set available, so first what I can do, I can create this type of individual derivatives using the small perturbation in each parameter, and then corresponding to these perturbations I can substitute back in my original equation of the uncertainty, and this entire thing can be done in the form of a computer program. Okay, so this is nothing but whatever derivatives we are calculating, these derivative rather than specifying in the differential form, if you are doing in the differential form, your computer cannot do differentiation. Okay, so there what you have to do, you have to in your computer, if you are solving the differentiation, you have to manually do. Okay, so here you are taking the help of computer. So when you are taking the help of computer, you have to represent your differentials in terms of algebraic difference equations, because computer can only do algebraic manipulation. So that is what actually is shown over here. So you can represent your partial derivatives and final uncertainty equation in terms of the algebraic equations, and these algebraic equations then can be simplified in the form of a computer program to calculate uncertainty in all measurements. Okay. Now comes one very important point. So whenever you are doing the experiments, say you have taken some readings, how you can decide whether your reading is correct? Is it a good data point or a bad data point? So say I am getting some values 25.3, 25.2, 25.8, say 26.9, 24.9. Now can you say me, out of all these readings for a single parameter, which one is bad data point? 26.9. So it means that if at the moment you don't know any statistical tool to segregate your good data or bad data, just from your thinking or your intuition you can think of that, okay, 26.9 is appearing too far from majority of the measurements, so let me remove this data point. Okay, but in real practice it may happen that this is actually the correct data. Okay, so that's why you cannot make these decisions just by looking into the numbers. What you have to do, you have to have some basis to decide whether your data point is correct or not. So one of the famous criteria is known as Chauvinet's criteria. This criteria is actually based on the standard deviation of the data and its deviation. So say you have taken 100 samples. If you have taken 100 samples, what you can do? For all these 100 samples, you can calculate the standard deviation sigma. Okay, and for all 100 samples you can calculate the deviation. Deviation is nothing but your individual measurement xi minus xm, where m is nothing but arithmetic mean. Okay, so likewise if you have 100 data points, for all the 100 data points you will be having unique arithmetic mean. Okay, for all these 100 data points you can calculate the value of deviation di, when you are calculating the value of di, you have to find that what is, for out of all these 100 values of di, what is d maximum. And if you take the ratio of d maximum by sigma, if the ratio of d maximum by sigma is greater than some specified value, then that particular data point is a bad data point. Okay, and if it is less than, maximum deviation by sigma is less than the specified value, then all your data points are nothing but coming under the category of good statistical distribution. Okay, so this what is that criteria? That is something which depends upon the number of measurements you are making. Say if you do 3 number of measurements only, then your Dmax by sigma of 1.38 is a critical value. If any deviation is above than 1.38, that particular data point can be actually discarded from your sample. Okay, and with the remaining data points, then again you have to do the same process, because once you are discarding that data point, your number of data points has decreased by number 1. So if that number of data points has decreased, then ultimately what will be happening? Your value of sigma and value of mean will also change. Then again you need to do this calculation with your remaining samples. Okay, so likewise you can see when your number of measurements are increasing. So when number of measurements increases, then of course the allowable deviation is also actually increasing. Okay, and typically whenever we do make the measurements, so if we do good number of measurements, then ultimately our measurements should follow actually normal distribution. Means majority of the readings will be coming through a single unique value, and then these will be distributed about that single value. Okay, unless or until our samples are biological. In case of biological samples, there will be actually growth of bacteria and numbers may grow. So then some other types of distribution such as Poisson's distribution, etc. will be applicable. But for majority of the measurements in our engineering practices, where we are considering that the fluctuations in measurements are coming because of the random errors, there actually our data distribution should follow the normal distribution. Okay, so based on the criteria of the normal distribution, this maximum deviation by standard deviation is actually considered as cutoff criteria to say which sample is statistically good or which sample is statistically bad. Okay, so one simple example is given over here. You have 10 measurements. For these 10 measurements, the value of di by sigma is given over here. So out of this value of di by sigma, maximum dmax by sigma is 2.046. Now if you check for 10 measurements, the specified value is 1.96. So it means this is my bad data point. So if I have to make other conclusions, okay, other conclusions means if I have to give that, say I have done 10 trials, out of these 10 trials these were my values, but ultimately I am taking the mean of all these values and I am taking that mean is my final representative data. Then in that mean, actually if I include this data, then my measurement will be wrong. So I have to remove this measurement, and then whatever remaining data is there, like 9 entries, for these 9 entries again I need to do this entire analysis. And if that is satisfying the statistical criteria, then after removing this point I can say that remaining 9 entries are nothing but true representative of the measurement. Then I can take simply the average of these measurements and I can tell that is my unique value for that particular parameter. Okay.
नंबर ऑफ रेटिंग अगर बढ़ा रहा है तो डेविएशन कम होना चाहिए, मेरे पास ज़्यादा डाटा पॉइंट्स तो यहाँ तो बढ़ा जा रहा है, तो चीज़ की कमी नहीं होगी तो ही।
No, this is not the meaning. The point is, when you have less number of measurement, okay, say you have 2 readings like this, what will be your standard deviation or other parameters? These will be statistically less significant. When statistics gives good accuracy, if you have large number of data points. Okay, so when you have large number of data points, then what will be happening? You will be having, say, significant clustering of data like this. So if you have significant clustering of data, then the zone in which your majority of the points are actually lying, it will be widening up. But defining this zone for very less number of measurement has to be very narrow, otherwise your measurement will be too much distinctive. Okay. This is a simple point. If you take two measurements, in two measurements, do you think that all the possible random uncertainties are accounted for in these two measurements? Not possible at all. Okay. But if you consider 100 measurements, so in 100 measurements, you will be finding that if all the types of random fluctuations are accounted for, means majority of the uncertainties are accounted for in data, you will start finding there is good number of repetition in your measurements. Okay, so unless or until you are measuring, you are not finding good number of repetitions in your measurements, it means you have not accounted for yet all the possible uncertainties in that measurement. Okay, so that's why upon increasing the number of measurements, you may get wider spectrum, but occurrence of number of repetitions of that wider spectrum will be actually more. So if number of such occurrences are more, it means you are able to account for the maximum number of the uncertainties. But majority of the time this happens that, say, your experiment is too much cost consuming. Your experiment is extremely time consuming. Say your experiment is taking 1 year to give you one data point. Your experiment is taking 1 crores of cost to perform it once. In that case, what you will be doing? You cannot go for 100 measurements or 1000 measurements. So you have to rely on lesser number of measurements. So when you are relying on lesser number of measurements, your criteria has to be more restrictive. So statistically, your criteria has to be more restrictive because it is not accounting for all the uncertainties which are taking place in your data. Okay. So that is the reason. So this is nothing but whatever this table is there, which you can use for deciding the critical value of the deviation by uncertainty, that is presented in the graphical form. So d max by sigma is given over here, and number of readings are given from 1 to 1000 on a logarithmic semi-log plot. So semi-log plot means you can see the wide spectrum of number of samples using this curve. Okay.
ये जो सर क्रिटिकल पॉइंट्स दिए हुए हैं ये 3 सिग्मा अप्रोच पे है.
Yes, these are based on considering the 5% level of significance. So of course I am not again going to discuss that. All these parts actually I have skipped from here. Okay, because now we need to start the next module also about the simulation methods. But all of you, if you want to know a little bit more about the analysis of the experimental data, so what you can do, I have one more course which is available in recorded form, that is experimental methods in thermal engineering. So in that course on analysis of experimental data, there are around 6 to 8 lectures, so you can refer to these lectures. Okay. Okay, so then we have this chi-square test of goodness of fit. So this is very simple method. Here what we want to see, based on the value of chi-square, we want to determine whether our two samples are correlated or not. Okay, so typically we calculate the value of chi-square as summation I varies from 1 to n, observed value minus expected value. So expected value, majority of the time you can know from your theoretical understanding of that particular measurement. Okay, so from theoretical understanding, say if you know the value of flow rate, in some pipe and then heat transfer is taking place. So theoretically you can have some idea, some expected value of heat transfer coefficient what you will be getting. And same heat transfer coefficient you can also calculate from the observed value. So whether your expected or observed values are having good match or not, that if you have to test, then you can utilize your chi-square test for goodness of the fit. So here one table is there which lists the value of f in first column and value of probability of occurrence of the events in different columns along the this top row. This f is nothing but number of measurements minus number of constraints. Okay, so depending upon the number of measurements minus number of constraints, you can calculate the value of f and you can calculate the value of chi-square. These are the values of chi-square. Corresponding to all these values of chi-square and f, you can calculate that how much is the probability of occurrence of in that particular data set. Okay, so if probability of occurrence of this data set is in the range of 0.1 to 0.9, then it is considered that your experimental data has good match or your observations has good match with the good match with the expected values. Okay, so one simple example is given over here. Say these are some type of defects which are being measured in the cups. Okay, so two set of cup samples are there. In first cup sample, say number of cups having defect 1 is 1, number of cups having 2 defects is defect number 2 are 2, number of defects having number of cups having defect number 3 are 3, and likewise for group sample are 5, 3, 3. This type of data we have. So we have in total nothing but 100 number of measurements. Okay, so out of all these 100 measurements, you can see that your number of defects are how many? 8. So 8 type of measurements you have, and in all these measurements what you are quantifying? Only the nature of some individual defect. So constraint is your defect. So 8 minus 1 is 7. Now by taking the value of f equal to 7 and considering that, say this is your expected value and this is your observed value, we can see whether these two samples are having good correlation or not. Okay, so of course whenever you will be actually applying this chi-square test, if the number of defects in particular cell, if number of measurement in a particular cell are less than 5, then it will not be giving a correct sampling approach. Okay, so that's why in order to make correct sampling approach, you can see that these top 3 measurements are having very less values. So what you can do, all these 3 type of defects you can combine together as defect number 1, 2, 3, then your total number of measurement in first sample will become 6 and in second sample it will become 11. Okay, so likewise you can combine this data and you may say that this is your new data set. Okay, in this new data set you can see all the individual values for each cell are above than 5. So if these are above than 5, then you will be getting good statistical accuracy. Otherwise your accuracy in your statistical analysis may not be proper. Okay, so using this, if you calculate the value of f, it will be 5. If you calculate value of chi-square, it will be 7.145, and if you calculate the value of probability, it is coming out to be 0.43. How to calculate the value of probability? Corresponding to value of chi-square equal to 7.145 and value of f equal to 5, you have to refer either you can refer this chart. So on this chart also you can locate. Here there is chi-square value, this is probability, and this is degree of freedom. Or you can refer to this table, and based on that actually, if you are getting your value in between, if you are getting your probability value in between 0.1 to 0.9, it means these two samples are closely correlated. Okay, so
अर्फ निकालने के लिए 6 - 1 किया है, लेकिन जो फर्स्ट अपना केस है उसमें तो 3 डिफेक्ट है, ठीक है।
yes, first में, so though we have 3 defects in the first, but how many number of cells we are having? Only. So ultimately our cells were, here our cells were 8 only, but in individual cells the number of measurements were less than 5. So if these measurements were less than 5, then I cannot like rely properly on the data. Okay, so in order to rely on data, just to take the just to ensure the good statistical accuracy, these sets we have clubbed together and considered as a single type of defect. So that's why we are using 6 minus 1 here.
इसमें ऐसे थोड़ा सा 10 से 10 और 6 वाले को एक साथ कंसीडर करें।
So our idea was to only club the values which are less than 5. Okay, because those which are 5 or greater than 5, that is considered to be statistically a good sample. Okay.
यहाँ constraint क्या है? पिछले slide में बताया था constraint
Constraint means whether cup is defective, discard it. If it is good, keep it. So only constraint is to determination of the defect. That's it.
पिछले slide में वो constraint है 30 तक का है, ये क्या कौन सा constraint है?
Here it is up to 30. This is not constraint, this is degree of freedom, F.
Constraint कहाँ दिखा सकते हैं?
It depends upon your requirement. Okay, it depends upon your requirement what you want to do. Okay, now say you have to plan one experiment. Okay, let's consider you all have studied say course on heat transfer. So you are asked to calculate, to design an experimental setup for calculating the heat transfer coefficient of a fluid which is flowing at certain velocity through a pipe, or that pipe is say heated externally. Okay, so what are the things you need to do to develop the experimental setup for that? Can you tell me?
Dimensions.
Yes, you have to determine dimensions, flow rate, flux, heat transfer. What else?
Property of fluid जो flowing हो.
So likewise, we may get thousands of this one. So our first task should be, we have to determine what are our primary variables. Okay. For example, if you have to experimentally calculate the value of heat transfer coefficient, we know that heat transfer coefficient is nothing but function of properties of the fluid, density, viscosity, it is function of velocity, it is function of thermal conductivity, it is function of specific heat, it is function of what else? Geometry. So it is function of so many parameters. Okay, but ultimately whenever we non-dimensionalize, then I say that Nusselt number is function of Reynolds number and Prandtl number. Okay, so it means that if I have to calculate heat transfer coefficient, ultimately obviously my aim will be to decrease the number of measurements, okay, or decrease the number of parameters. So then I will be presenting my results in dimensionless form, and moreover dimensionless form gives the more generic nature of the results. So that's why in order, so it means Nusselt number I need to calculate, this is my output parameter, but Reynolds number and Prandtl number are input parameter. Now in Reynolds number and Prandtl number, you can see the definition of Prandtl number is mu Cp by K. Now if you fix that, whether you want to do your experiments with air, or you want to do your experiments with water, or you want to do experiments with some other fluid, say some refrigerant. So you have to decide what is your requirement. You need to calculate heat transfer coefficient for air, water, or some any other type of oil or fluid. Okay. So once we have fixed the fluid, my value of these parameter has already frozen. Because this is something all are nothing but fluid properties. So these fluid properties are now fixed.
CP can be deflected because of temperature.
Yes, so if you have to account for that dependence of temperature on Cp, before that you have to decide that what is your temperature range. Because depending upon the temperature range, it will be known to you that whether in that range of temperature your Cp is changing significantly or not. Okay, so and moreover, even if it is a function of temperature, you need not to do experiment for this, because for majority of the standard fluids, the values of properties as function of temperature are already available to us. Okay, so this also we have to think that we should not do experiment for everything. Say the things which are just known to us, for that also if we are wasting our time, we are wasting our money. So that's not the good plan. We should do experiment only when there is a true requirement. Okay. So just for the sake of experiment we should not do. So that is considered under the laboratory, like usual teaching laboratory experiments, when you have to learn some method. So say my properties are now frozen. Then I have this Reynolds number. So Reynolds number is rho V d by mu. So now I need to decide that the heat transfer coefficient I need to calculate in what diameter pipe. Okay, what is my requirement of the size of the pipe? So it means I need to decide D. But D is something which is not a measurement quantity. This is a decision based approach. Whether you want to study heat transfer coefficient in micro channels, macroscopic channels, or even large diameter pipes. So that is your requirement of the system. Okay. So D is coming from there. Rho and mu already we are knowing. So only parameter now we have is V. Once we have V parameter, then also we need to decide whether we want to do our experiment in the laminar flow conditions or turbulent flow conditions, or we need to take up both the regimes. So once I have decided D, I have decided fluid, then I need to check that, say what range of Reynolds number I want to do experiment. Say I need to do experiment from 100 to 10 to power 5. Then accordingly I can calculate the minimum and maximum value of the velocity. Once I have calculated minimum and maximum value of the velocity, corresponding to that, once I know the value of average velocity, I can multiply with cross-sectional area and calculate flow rate. So from here I will be getting one independent parameter, flow rate. Okay, which I need to say measure. Then of course this I have written is a functional relationship. But here if you have to exactly calculate the value of heat transfer coefficient, then you need to write equation of heat flux equal to H times T wall minus T fluid. Okay, so it means you have requirement of measurement of the fluid temperature, you have requirement of measurement of the wall temperature, and you also need to control heat flux. So now that is also our requirement. Now question can come whether I want to do an experiment under the constant temperature condition. So I want to consider a tube which is maintained at some constant temperature and then fluid is taking heat from that tube. Or I want to do experiment under the constant heat flux conditions. Then I need to make some arrangement where I can control the heat flux of the pipe surface, and then accordingly I can calculate different parameters. Okay. So it all depends upon requirement. So majorly our interest is to measure temperature. So along with the flow rate I can write my second parameter as, and majority of the time, though here if my only interest is in heat transfer coefficient, then pressure I may not be interested. But say if I also want to calculate that how efficient is the pumping process, then I may have to make measurements of pressure as well. So say these are the parameters which we have identified. So when we identified these parameters, after that we need to see what control must be exerted on the experiment. So in terms of control, whether I need to control the constant temperature experiment or constant heat flux experiment. So depending upon that I have to decide. Okay. Then what ranges of the primary variables? Now my say final requirement of Reynolds number is from 100 to 10 to power 5. This requirement has told me that what should be the corresponding values of flow rate of the fluid. So I have known the range of flow rate. Then I can also decide that from what heat flux to what heat flux I want to do measurement. Accordingly, I can decide my temperatures. From, or say if it is a constant pipe surface, then also say I want to do measurements from 100 degrees Celsius pipe surface to 800 degrees Celsius pipe surface. So then I have decided the range of temperature which I need to control. So accordingly, this. After that point is how many data points should be taken in the various ranges of operation to ensure good sampling of data, considering accuracy and other factors, considering accuracy of the instrument and other factors. So once you have decided that what is range of measurement, after range of measurement, now you can refer to the data sheets of different instrument. So different types of flow meters. You may have a simple venturimeter based flow meter, you may have a turbine flow meter, you may have ultrasonic flow meter, okay, you may have electromagnetic flow meter. All these instruments will be having different range of accuracy. So you need to choose different instruments, then you need to perform uncertainty analysis, and from the uncertainty analysis you have to decide that which one will be giving you good amount of accuracy. Then you can choose that. But of course, when you are choosing that, you have to also decide your cost. So this is the about the accuracy and how you can decide accuracy by doing uncertainty analysis. Say if you have chosen some instrument which is giving you 50% uncertainty in your output parameter, is that a good experimental instrument? No. You have to go for some with good uncertainty limits. Okay, so that is something you have to do. Then next point is whether dynamic measurement is needed or not. So what do you mean by dynamic measurement? No. There can be two types of situation. One situation can be a steady state experiment. Okay, in a steady state experiment, say you have maintained, you have run the setup, you have allowed it to reach steady state, and at the steady state just you want to measure what is your data point. Your second requirement can be you want to know that when the system is moving from initial condition to its steady state, then what path it is taking, how it is behaving during that time. So then your measurement will be actually dynamic. So time dependent measurement will be dynamic. So when you have time dependent dynamic measurement, corresponding to that, your frequency response of the instrument should be sufficiently small in comparison to the time scale of the physical phenomenon which is happening. Say in your setup, physical system, temperature value is changing by 5 degrees in 1 second, okay, in 1 millisecond. But your instrument's response time is say 20 milliseconds. Then what will be happening? You are missing the data of 20 milliseconds period. So that is not a good frequency response of the instrument. Okay. So depending upon that, you have to decide. Say in your, if 1 millisecond your data point is changing, at least minimum requirement is there that your frequency response of the instrument should be 1 millisecond. So this is very simple. For example, if you use a thermometer, so when you dip a thermometer in say hot water, it does not immediately show you the temperature of water. It takes some time to reach there. Okay. So if you are only interested in final temperature of that water, then there is no problem. But say if you have dipped thermometer in some water container whose temperature is changing continuously with time, okay, and you want to record that change of time, then your thermometer should have sufficient response time in order to respond to the temperature change, okay, in comparison to the time scale of that physical phenomenon. Okay. So that's why when you have dynamic measurements involved, then your selection of the instrument becomes more critical. Not only the selection of the instrument, when you are doing the dynamic measurement, in your static measurement, what you can do? Say steadily your system is running. If you have 10 sensors mounted there, you can first just record the data of first one. You can note it down in your notebook from say some digital display or analog meter. Then you can go to next one, then you can record the data of that one. Okay. But whenever you have dynamic response and you have multiple instruments mounted in the setup, then you have to simultaneously record the data. So when you are simultaneously recording the data, you have to use some data acquisition system. When you are using the data acquisition system, again it may happen that say you have correctly chosen your sampling frequency of the instrument, but whenever you have chosen your data acquisition, that is not having that much frequency response, then what will be happening? Even if it is giving you, say you have simply changed that, okay, show me output of, in interface of data acquisition system, you have mentioned that give me output of 10 samples per second. It will give you 10 samples per second, but it may give all the 10 readings as a same value, because it is not able to respond to the input it is receiving from the instrument. So whatever sampling frequency you are considering for instrument, same should be applicable for data acquisition system. And in data acquisition system also you have to understand this point very carefully, that say if data card of a data acquisition system is saying that its frequency is 100 hertz or 1000 hertz, and say it is having 10, it can measure 10 samples simultaneously. So when you will be using only one measurement sensor, then it can give you maximum of 1000. But if you are using 10, then per sample you will be getting only, per sampling port you will be getting only 100. So you have to also decide that how many number of high speed readings you are requiring. Accordingly you have to choose your data acquisition system also. Okay. Okay, after you have chosen the instrument, then are the instruments available commercially? Of course you have to tell that, say agar if some instruments are not available, then you have to construct. So for example, we don't have any instrument available for measurement of heat transfer coefficient. That is why we have to develop the setup for measurement of heat transfer coefficient. If we have some standard instrument available, I will just insert in the pipe and then calculate. Okay, but we know that there is no standard instrument available for measurement of heat transfer coefficient. But we know that for flow rate we have a standard instrument. So then I need not to design again the system for measurement of flow rate, because from measurement of flow rate I can take simply a commercially available device. For measurement of temperature you need not to design the thermocouple by your own. You can take from commercially available thermocouple and then you can use that. Okay. Then safety precautions. This is typically involved if you have, say, some hazardous operation. Say you have to do experiment with some gas, okay, and then there is some leakage of that gas which is not good for your health. Then what will be happening? Okay, then financial resources. This is important. Say what you have done, you have selected the instruments which are costing 1 crore and you have 5,000 to do the experiment. So then your selection of the instruments is not proper. That aspect also you have to keep in mind. Okay, and what provisions have been made to record data. So of course when you have steady state measurement, then you can simply have analog displays or some digital displays, multi-channel digital display, and then you can record data. But if you have simultaneous measurement, then actually it will be. So if say for some parameter you need to do computer reduction of the data. So this is required when you are actually taking some corrective action based on the input data. So that is something which may be applicable, say if you are in a chemical industry, you have measured the temperature and you found that temperature has increased too much. Then what you need to do? You need to control the amount of fuel you are supplying to the system. So there if it is required, then you have to also do computation simultaneously and then take the appropriate actions. Okay. So this is the generalized experimental procedure I have already explained to you. So you can go through this block diagram, and then this is generalized procedure of data acquisition system. So instrument measures the physical property. Physical property is subjected to the instrument. Then instrument gives some signal. That signal goes through input circuit of the instrument. After signal conditioning, you will be getting some output which is transmitted to the processing unit, and then ultimately you get a display of that output. So if you have multi-channel system, then the whole system is actually repeated for multiple channels, and that you need to perform simultaneously. Okay, so you can go through this, and moreover, the example which I have taken over here about the measurement of heat transfer coefficient, this I have explained in detail in my course which I talked about experimental methods in thermal engineering. So I just suggest all of you please read lecture number 30 of that course. So it is available on YouTube, experimental methods in thermal engineering. Please go through the lecture number 30 of that course, because that gives you the entire details of the selection of instruments, uncertainty analysis, and even your final data sheets, what data you need to extract for measurement of the heat transfer coefficient. Okay, please go through that particular lecture.